panel discussion between the 3 laureates and the 2 somewhat younger scientists. If I have done my research correctly, we're actually spanning 5 decades, from the 1940s to the 1980s by birth. So it's not quite 5 generations, but you see a PhD supervisor and his student here, and clearly I could be Conny's student as well, while I'm not. But yeah, so we have an intergenerational discussion here, and in particular, we'd like to hear your view on the future. I mean, we had a very broad, within the field of stellar physics, coupling to astroseismology and helioseismology, a very broad range of topics and talks today, which were very inspiring, I thought. And we would like to discuss, where do we go with this in the future? What do we need? What do we not need? Because we cannot have it all. There's competition. And maybe you have ideas about this.
Yeah, well, I guess, I mean, one thing I was curious about is we've heard about so many applications of seismology in general. Is there anything that has come out of this field that you find particularly surprising? I mean, from the beginnings of discovering that we could do this in the sun and applications to other stars, is there something beyond that has just really, you found amazing that we've turned this into a whole new field?
Any one of you?
Well, let me start also quoting what I said to the journalist when I was interviewed when the Kepler was launched. And he asked what I would be most surprised about. And my answer was that, well, I would be very surprised if our simple models of stars worked at all. and one surprise actually is that they are not too bad, these models, in terms of comparing with the observations. And of course, as Conny would say, the very interesting part, and what we all love, is when the models don't work, because that's when we're learning about new aspects of the stars. And we have plenty of that. There's plenty of things that need to be understood much, much better. And in some cases, discrepancies that look subtle in one star could be huge when applied to other stars. And that's really where we're heading.
My single word answer is we didn't understand internal rotation of stars.
That too, but we didn't understand lots of things. Oh, sorry. I'm not a real astronomer. I'm more of a physicist, really, and I'm interested in the physics we learn from stars. And so, although I've dabbled in astroseismology, most of my life has been with helioseismology, the sun. And as I showed this morning, although Jørgen is saying that the results of helioseismology and astroseismology are so close to the models, and in the models we were hearing just now from Andreas, 5%, 10%, I was showing 0.1%. Now that 0.1%, I showed you a picture, it's not random. The structure there. And from that structure, you can learn about the physics of the material that makes the stars. You can learn about the nuclear reactions. And you can learn, of course, which is what Conny wants, about things like meridional circulation that mix materials in stars. And now it becomes, of course, astronomy. Mm-hmm. That's a very, very small effect. But it's fine to have models, computer models that predict it, but we want to know if it's right or not. Mm. And for that, we've got to measure it. And I can think of no other way of measuring it than through seismology. Mm. But it's a very tiny effect. Mm-hmm. Mm-hmm. And so what I want to see in the future is more work on the boring star, the sun, because we've got so much better information for that from that star that I think we mustn't forget that when we go off into all these wonderful exotic stars that you love, Conny.
Mm-hmm. Of course, I agree.
But if you then look at this boring star, the key point there is that we are doing physics. We are doing the thermodynamic and radiative properties of material in the sun, and that doesn't work at all. We can see that now. And things actually in that sense are more interesting than they were 30 years ago when we had the first good data, because other things have changed in the meantime. We have better measurements of the solar composition, and that actually has increased the discrepancy between the sun and the models, and that discrepancy then comes from our lack of understanding of atomic physics. I mean, there's a very close connection between, of course, the physics of matter in the sun and our models, and then what we observe with heliososmology. And so what we can do here is to learn about plasma physics at a very, very detailed level, and a level that's much beyond any physical understanding that we have of these processes.
But what are the bottlenecks? I mean, the revision of the solar composition took place 15, 20 years ago and has been strengthened ever since. Why have we not solved the solar modeling problem? Why is the standard? I mean, okay, one clue I could give, of course, you will jump on it right away. Why is the standard solar model still a non-rotating model?
Well, the so-called standard solar model is a non-rotating model because that term was invented by a man in Princeton who never thought of rotation. And so I don't think that's a useful question.
Okay. But why are the dominant solar models still?
Well, for example, you're talking about the chemical composition. I think what you meant by the chemical composition, I may be wrong here, and I think maybe to some extent what Jørgen might have meant, are the latest, perhaps more accurate, but certainly different measurements because of the better way of analyzing the structure of the photosphere.
Correct.
And so those are surface results, not necessarily the composition of the solar interior. And so one of the things that I think the data that we have may well be adequate to push forward, but there hasn't been enough work on it, is to start learning at least the relative abundances of the most common heavy elements, carbon, oxygen, nitrogen, that you can get from changes in the equation of state, even at the level that we know the equation of state today. It would be wonderful to know it even better, which is what Jørgen wants, but I think astronomers would quite like to know what the chemical composition of the sun is, at least the abundances of those elements that are important for determining opacity, which determines what's going on in the radiative interior. I think the physics for that, the atomic physics for that, is well enough known for us to make headway in doing a better analysis of the observations from MDI and SOI from Stanford, data that we already have but haven't yet made enough use of. There's always a tendency to go up in space and get new measurements. I remember making. I remember one of the things that really impressed me once was when I was on an advisory panel for setting up the SOHO space mission and advising NASA people that all we needed to analyze the data properly were 5 versions of the biggest computer in the world. And they were horrified. Whereas I thought that was good news, because by the time the spacecraft went up, computer technology would have increased so much that that was a small result. And of course, Moore proved that to be correct. Nowadays, a lot of the analysis you can do on your laptop. So I think it takes more human thought to decide what to do with the data we already have.
We need to keep thinking and observing, one of the speakers said. I think it was Laurent. How do the solar neutrino observations of the neutrinos coming from the CNO cycle tie into this?
Well, when that's understood even better, it's going to be used for estimating the chemical composition of carbon, nitrogen, and oxygen. That's correct. The core. And I don't think it's come together well enough yet, but it's going to. And I think that's going to happen in the foreseeable future. And I look forward to that result. Right. I did actually write a short paper predicting what the result will be, but
Well, what are some of the other major holes that you all see, observations that are being underutilized or key problems that are not being, pursued enough that can be done with seismology?
Well, for the youngster in the panel, among the three, I mean, I'd like to hook on Andreas' talk and really move to clusters. For the young stars, this is critical because as it stands, we don't have, I think nobody has had the courage to look at open clusters of like a few 100 million years and the red giants in them, but backtrack to when they were born, because physics that we're missing has a cumulative effect across the evolution. And so I would like to, for that reason, go to young open clusters where we have both my favorite pet stars, fast rotators, but also red giants, and explain them at the same time. So that's why I was trying to convince the audience this morning why I want to move to clusters, because binaries are great, but that's not even enough in terms of
I don't know how young you want your clusters to be, but when you mentioned the red giants, do you mean what happens when they go off the main sequence?
Yes.
Or do you mean when they're coming down towards the main sequence, they're collapsing from the interstellar medium?
That is very difficult.
I know.
Because it's a matter of detecting the oscillations. But if you look at the Kepler clusters that were observed for 4 years, we are now discovering all sorts of gravity mode oscillators on the main sequence, while I think it's correct to say, and I'm looking at Andrea, that so far you only have looked at the red giants and explained them. And so I'm sure these red giants, when they were young, they were super fast rotators.
Oh, yes.
Whether one likes it or not.
Yes, yes.
And
Well,
so
at least on the inside.
the cumulative effect of that rotation, we haven't put our act together in explaining those.
As far as the basic evolution from the main sequence is concerned, it's been ignored totally.
Yes, and so I want to improve upon that.
Lovely. Good. Well, I look forward to that if I live long enough.
Yes, I will try.
Good. Thank you.
I think that there's one point we should also keep in mind, and that's politically a bit difficult. We should not. We get overwhelmed in some sense with data because we have all the data from the TESS mission, and in a few years we'll have all the data from the Plato mission. And we shouldn't forget that we still have a huge amount of Kepler data that hasn't been fully used. And Kepler data, even with Plato, for some stars, is going to be absolutely the best we have. And so we really need to keep working on those data and not forgetting. And of course, we have to keep working on the sun. That's a given. But there are stars there that we really are able to study in much more detail. And some of the processes that we are looking at are extremely subtle and really needs very careful work on individual stars. And a very important issue that has come up here is mixing processes in the cores of stars, which are absolutely crucial for converting any kind of measurement of a star to an age. Because what we measure is really how much hydrogen has been turned into helium, and that relation of that to age depends on whether additional hydrogen has been mixed into the core. So that's an issue that we don't understand physically, and that also has to be modeled better, but also in terms of analyzing the observations is going to be crucial.
So advanced tools, machine learning, AI will not solve the problem?
Real human sort.
We need another 40 PhD students.
That's right, exactly, yes. Absolutely.
Yeah.
And we need to combine that then, of course, with very detailed modeling and including 3D hydrodynamically models to the extent that we can actually apply that to the interior of stars.
It's almost an argument for not launching any more spacecraft, because there's so much more to do. But to do that, we need the money to support more young people.
Yes.
But
with bright ideas.
We do need Plato. As you see, it's
almost built. No, that's still there already. I said more compared with what's already been agreed with.
We also want Haydn. Don't worry, Andrea.
But it's true.
Fund giving organizations want to put money into new hardware that goes into the newspapers and makes them look better. They don't want to pay people like us. They don't need to pay us anymore, but the young people, we need them. They're the future.
Yes, absolutely.
But a related question would be, how do we identify talent?
Oh.
You mean human talent?
Yeah.
Okay.
I mean, Conny, I know you're a big person on the European scene in terms of research funding, the EC and the ERC, and what is your take on this?
I'm fighting for much more funding to be put in blue sky research for the moment. I have literally a task that is ongoing now for 1.5 years at the European Commission, where we must make it clear to politicians and CEOs in industries that everything starts with fundamental research. And so I think there are good arguments also on the economic side if they need to or want to hear them. But there is nothing as important as human activity, just based on pure curiosity of kids. Please help me in striving for that.
So catch them early, is that your message?
Yes, and make sure that they can follow their dreams and get an answer to the curiosity. That's what we did.
Yeah, absolutely.
And that's critical.
Absolutely.
And it's becoming harder and harder to also allow for the answers to take a lot of time. You know, in the if I think back, I really started at a time when people did not believe that astroseismology would ever work. I've heard it very many times, but if you are persistent and if you allow people to be persistent, and you know, sometimes it takes 20 years to find something, and that's very hard to sell at a political level nowadays. So that's my quest, to fight for that on the one hand. On the other hand, we do have to go to school kids and to give them examples and to trigger their curiosity and give them self-confidence that they
be role models
yeah.
for them, essentially.
Yeah. So that's
May
important.
I just add to that?
Yeah.
Having sat on committees that give money, as we all have, if that money comes from the government, you have to justify it. The best committee I've ever sat on, and after I formally retired, I stayed on that for quite a long time, even though I gave up all the government ones, was a committee from private money. It was from the Crown in Britain. And there, one didn't have to justify what one did. One argued with the rest of the committee, and one might well say, because this particular person has done something, said something, my gut tells me that we should pay them. Whereas if somebody has passed all the exams and got lots of money, lots of best from this university or whatever, you say, well, no, we don't have to pay that person. They'll get a government grant. And if you then look at the results of doing that, you wait some years and see how well they've done. I would say on average, by that technique, you do about the same as for the government grant. But the distribution is different. Half of them fail and the other half are brilliant. And I think that's the best way to find the best talent.
So being successful with all these funding agencies, you have to develop your pitch in some way that is, accessible to the panel, but also you want to develop a way of communicating your science that is accessible to the young people. Can you talk a bit about, you have had great metaphors for, listening to the stars. How have you developed that over the years to really be able to communicate very complex physics to even young people and school children?
I've enjoyed talking to 5-year-olds in schools. You think of how you're going to explain it. Yes, you produce metaphors, you produce analogies. How is it that that the nuclear reactions in a star increase as the temperature goes up? You can relate that to cooking a cake. And the children understand that things are different. One of the best experience I had was with at a school that my granddaughter went to. She's up there, actually. When I was explaining this to some young children, and I said that, when the cake, your mother puts it in a cake into an oven, it looks different when it comes out. And one little boy piped up and said, "Yes, it comes out black." He understood.
Very obvious.
Yeah, so actually, explaining to young kids, my youngest audience was 4-year-old, was my son. That's one thing. Another thing is that maybe that's also a bit of a generation effect, but I think people pay more attention now to some training in communication because we have more diversity perhaps in the audiences. So that's an aspect, and some people like to learn about doing that, and others don't like it at all. So my advice is always like, well, you have to do what you like, because then you become good in
absolutely.
it. So never enforce it, but appreciate that some people take training in it. I mean, and you learn as you move along to find better analogies and more accessible ways of showing things.
But you said that some people don't like doing that.
That's right.
Well, if you can't explain it to a young child, you don't understand it.
Then you lack something.
Yeah.
I agree.
Exactly.
Yes. But that's something else than making a video in front of a camera, which might be scary for some people.
Yeah.
Oh, yeah, is that what we're doing now?
Yes, that's right.
I'm terrified.
So the young kids are way easier to train yourself, I think, than cameras. But we need all kinds,
But then also that's something to keep in mind when we educate our students, that they should also receive training in presenting their research and their excitement, transmit their excitement. And of course that could be helpful because they're closer to the kids that we want to approach. I mean, somebody old like me coming to talk to high school students is fine. We had a very good session actually in Lund doing that. But a young person like you might be closer to explaining why this is so much fun and why they should go into doing that.
More relatable.
Yeah.
Potentially.
Yeah, that's right. Yeah. And of course, gender also comes in here still, unfortunately. We have to work on that.
Okay, let's assume we have the talents, we have the students. Of course, funding is limited by nature. We live in an era where we are aware of or even planetary limitations. But let's think about our organizations, our institutes. Are they optimally set up for driving the science that we want to drive? Our institutes of
course not.
Of physics or physics and astronomy.
Of course not.
I think Douglas is very. You like the connection to mathematics very much, for example.
Oh, absolutely. Yeah. Yes. Well, I mean, in my country, mathematics and astronomy were the same. We have one of the oldest chairs in my oldest professorships in my university is a chair in mathematics and astronomy. It is now held by a pure geometer, and there's no astronomy expected from him whatever.
Actually, it's
other connections. I mean, IT.
Yes, but I think all three of us love mathematics. Actually,
absolutely.
And so got extensive training in mathematics, which is in this field.
Your first degree is in math, right?
Yes.
So is mine.
Yes.
Yeah. So is mine.
Yeah. So I mean, it's probably not a coincidence, although it's small number statistics. But the connection between astronomy and mathematics is very natural for me. And so this is also something that when we were discussing with the school on Monday, that I think came out in a natural way, because the questions were really both about mathematics and about astronomy and how they relate. So that is really nice. Of course, we live in modern times, and we cannot ignore that a lot of what we do is thanks to a lot of computational power that didn't exist half a century ago. But still, we are looking at tiny little details, so to speak. And so it's fantastic to have machine learning to help us find the stars. That's absolutely true. But once you have the best stars, I still want to look at the detailed modeling with my neurons and not with a neural network. But I'm a bit old-fashioned already, maybe, compared to our youngest panel member here.
I was just thinking that because in Cambridge, on a Wednesday night in winter, when it gets dark, we open up to the public, who can come and look through the telescopes. They would rather look through a 19th century telescope than they would having a much better picture on a screen that's broadcast from the world's biggest telescopes. They can see that in the books. They want the photons in their eyes.
Well, we all spend on average 6 hours looking at screens these days.
Some
Maybe
people,
not you,
some
Douglas.
people do, but I don't.
Talking about the average in Sweden is 6 or 7 hours of screen time nowadays.
Yeah.
So that is fully saturated, I would claim. Yeah.
Well, we're moving a little bit away from your question, which is fine. But
The institutions.
one thing that we should also maintain is just the basic fascination with stars and with the sky, and try to get people out where you can actually see the stars outside the cities where it's really dark, and that's something that we're also losing. Many people would not have seen the Milky Way with their own eyes, and that's a loss that we have to try to work against.
I might point out that when I started research, I did do some work on stellar oscillations. We called them pulsations in those days, Cepheids, because for reasons that Andrea told us just a little while ago. And then I had a student come who really pointed out that I didn't see things in the sky. I was this guy, actually. He said, well, if you worked on Cepheids, where is Delta Cephei? I had no clue. So he took a photograph of the sky and gave it to me.
Yes.
Should we open up the discussion to questions from the audience,
Yeah, I think
potentially?
we've got about
Maybe
5
there are
more
some questions
minutes,
left
so-
that remained unanswered during today. Saskia?
So my question is actually, if we want to look into the future, I would think we would look into also another parameter space, one way or the other. And I was wondering if you have any thoughts, what kind of parameter space would be most interesting to move into in the next 10, 20 years?
Is that a question to me or in general?
I hope it's to you.
Yeah.
Okay. You want me to start?
Oh, sure.
Parameter space opened up by Uppsala. For a person who works on massive stars, we really have to get into the more than one star situation. And that's a huge parameter space that opens up at once, because you have all the orbital parameters that come into play and the tides. And we haven't really done very much about that, to be honest. And this is absolutely necessary. So I'll amuse myself with that the next 10 years.
Well, I think I'll go in the opposite direction.
That's fine.
So, and that's also a matter of being old. I think the parameters I would like to move into is accuracy, precision. Certainly, I mean that's the basis of everything. But also in terms of more accurate modeling, really exhausting the accuracy of the observations, which is huge, and use, as you said, also apply that to specific targets and really learn about the physics on that basis of the stars, and the basis of that would be the solar data that we have and are still accumulating, the Kepler data, and then eventually, if I live long enough, the Plato data when they get to the same level of accuracy as Kepler has now. But that's going to take some years.
Well, as the oldest member, and therefore the most backward, I suppose, what I see is that having learned about the accurate mathematics of ellipsoidal figures of equilibrium under gravity that took place the late 19th century, right up until Chandrasekhar, the middle of the 20th century. I see that that beautiful work has very little directly to do with what you want to study. That's so far away that I feel totally incapable of knowing where to go. So I'm going to stay where I am, where it's safe.
Okay.
I mean, future themes in the coming end of this decade, next decade, we have two major instruments coming up. We mentioned the ones that are specifically for this field of research, but then we have the ELT, seeing first light this decade, and we have SKA being built next for the next decade. Will they impact on this research?
SKA, yes, I couple that to compact stars and radio emission of exotic things, but that's because Paul Groth is in the audience. And so in that sense, that's an area where I think it could point us at sources that are behaving differently than others. And then we could go to to see if there is any seismic signal from them. That's what I think could be happening. These are all sky surveys usually also, or big portions of the sky. I forgot your first question, but anyway.
ELT and SKA.
Yeah, ELT, yes. Yes, well, ELT.
For the follow-up.
For the follow-up, of course, that couples to Vincent's talk on planet-star interactions. That's critical. But of course, the exoplanetologists want centimeter per second precision. And that's great, because they can have their planets. We will have our stellar oscillations at that level. And then we can look at higher degree modes, actually, for distance.
Getting the time sequences at the ELT is going to be hard.
No, we don't need that, because the frequencies will come from Plato and from TESS, and we impose them on the spectroscopy.
Oh, okay.
And that's the way to identify high degree modes.
Okay.
And then you can do a lot more. That's back to my PhD roots.
Very good. Very good.
Well, if I may dream, and then here we're talking about long after I'm gone, there have been projects to observe oscillations on stellar surfaces, allowing to observe higher degree modes also in solar-like stars. And that would be a hugely important way of studying the internal properties of these stars and finding the tachocline, the rotation details in these stars. And technically, that's absolutely feasible. Money-wise, that's a different question, but it's going to happen one day, and that is going to be extremely interesting. And some of the young people now here might make use of those data eventually.
We have one more question from the audience. Yep.
Hi, everyone. I said it a little bit during my talk, but I think, personally, and I maybe speak for other people here, I'm very grateful for the contributions that all of you have made to the field. And I think on the personal level, for me, especially to Conny, who has sort of shaped my career in many ways. Now that you're sitting here winning this very well-deserved prize, I guess I wanted to ask if you have any sort of career moments you're most proud of or advice you want to impart on sort of the younger generation.
Oh, yes.
That made you successful in what you
Well, for me, that's simple. I actually placed as a last slide in my Lund talk on Monday a picture of my 43 PhD students. And I'm most proud of them because they have brought me where I am by triggering curiosity and by keeping me going. So I need young people around me to function optimally. So that's why I'm so grateful to them. And they were, they're my most proud slides. I always use it, and then they say, oh, there she is again, she wants another picture. But that just for me keeps me going and keeps me alive and kicking. So thank you, Vincent. And thank you, Saskia. And thank you, many others in the auditorium.
Well, if I should mention the most important points in my career, there are many, but I think really the most important point was the day when I bumped into Douglas's office unannounced and said I would like to do a PhD with him. and he didn't kick me out. And so my recommendation to young people is to be brave and do that. I mean, don't be scared to talk to what they look at might look like remote important people. And my recommendation to somewhat older people is to accept these young students that come in and want to talk to you and try to find out whether they might be interesting and might be worth investing some time in, and something interesting might come out of that. Plus some very good friendship, which is also very important.
Well, one point since you mentioned that, I should say
you have the final word, then we give the word to Sophia.
When this man first came to my office, then I'll not say what I was going to say afterwards, I'll just say this. Didn't know who he was. He said he wanted to do some research with me. So I wanted to try to find out what he knew. And before I got into any physics, I thought I'd just talk a bit. I mean, he said he was Danish, so I thought, who's the best Danish astronomer I've met personally? It was a man I met in New York, and he was introduced to me as Strömgren. And I thought, well, he must know Strömgren. And I started saying that, and he had never heard of him. He didn't know what it was. And then I started saying some of the things that Strömgren had done. And his eyes lit up, and he said, "Oh, Strömgren."
Okay, thank you very much for this discussion.